Welcome friends to my channel. Now on my last lecture I have told about a few numerical problems related to conservation theorem. Okay. Now in my today's lecture I shall going to discuss few other numerical problems. Okay. So let's proceed. Okay. So our first numerical problem of today's lecture is that is problem number 1. Given that if this equals to minus k by r square r cap, show that angular momentum is constant. Okay, we have to show that L is constant. Okay, we have to show that angular momentum is constant. Okay, now we know that angular momentum is what? Angular momentum we can write as L equals to r cross p. So if we differentiate this, we can write r cross dp dt plus this is dr dt cross p. Okay, fine. So this is r cross, this is f, and this is v, and this is mv, that we can write mv, so this term is 0. Fine. So the term that left is r cross f. Okay, so what we this is r cross, and this is given minus k by r square into r cap. Fine. So r vector cross k by r square, this can be written as vector r by mod r. So again r vector cross r vector is 0. So kindly ignore the noise which is coming from outside.
এবং আধারকার সকালে পদাবলী কীর্তন পুত্রবঙ্গ মুহূর্ত বিদায় ও হাতে মহোৎসব পালিত হবে।
So we have seen that for this particular problem the angular momentum remains constant. Okay, so this is our numerical. Okay, so just simply write the expression of L, then differentiate with respect to t, and then just substitute the values and rearrange, we can get to the result. Okay, so this is the first numerical of today's lecture. Okay, so let us move to the second numerical of today's lecture. Okay, so let us take the second numerical, that is given that if this equals to I cap yz j cap zx k cap xy. So we have to determine whether this force is conservative or not. It's simple. Okay, so we have to find out curl F. This is simply I j k del del x del del y del del z yz zx xy. So this is simply del del y of xy means x minus del del z of zx means x, plus this is del del z of yz, this means y, del del x of xy, this means y. This is del del x of zx, that means z, del del y of yz, that means z. So this is simply 0. So we have found that the curl F is 0, that means F is conservative. F is conservative in nature. Okay, so this is the second numerical of today's lecture. Okay, so Now let us move to another issue which is very important. Okay, that is the center of mass. Okay, that is center of mass. Okay, so the first question that arises, what is center of mass? Okay, so let us first express this. Okay, we consider a system of n particles. Okay, say there are n particles in a system, first, second, third. Okay, and there are n number of particles. Okay, this is the origin. Suppose this is the particle of mass m1, position vector is r1. This is say m2, position vector is r2 with respect to origin. This is m3, position vector is r3. Okay, and this is say the center of mass. Okay, and this position vector is say rcn. Okay, so then if the position coordinate of center of mass with respect to this origin is rcn, so it can be defined in this way, that is m1 r1 plus m2 r2 plus m3 r3 plus dot 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 by m1 plus m2 plus dot dot dot. That means this can be written as sum over I mi ri by sum over I m. Okay, so we consider a system of n particles. Say the particle of mass m1 is whose position vector is r1 with respect to origin O. Particle of mass m2 whose position vector is r2 with respect to origin O, and so on. So if rcm is the position vector of center of mass with respect to O, then it is defined in this way. That means we write it capital M, entire mass of the system or the body, entire mass of the body. Okay, so this is how center of mass is defined. Okay, now if we look back into the motion of center of mass, then from that motion we will easily explain what is center of mass. So at first let us discuss the motion of center of mass. Okay, at first let us discuss the motion of center of mass. How? That is, center of mass can be defined in this way, sum over of mi by m. No problem. So what will be the velocity of center of mass if we do differentiation with respect to this? What we get? This is simply mi ri dot. Okay, now again if we differentiate this with respect to time, we will get the acceleration of center of mass, which is nothing but what? This is mi, this is ri double dot. Okay, and this is what? This we can write as dpi dt. Okay, this we can write as dpi dt. So we know the position vector, we differentiate this, so first we get the velocity and then we again differentiate it, we get the acceleration. So that can be written in this way. Now this is simply 1 by m and this is simply fi. So from which we can easily write m into a into cm. This is simply write as fi. Okay, now let us see what is fi. Okay, what is fi? That we previously, that I told, that total force acting on the ith particle. Okay, so fi, that means the total force acting on the ith particle. Okay, so there are two parts. One is Fi external and another is Fi say internal. So there are two forces, one is externally applied and another is internal forces. Now we all know from Newton's law that internal forces cancels each other. Say this is one, this is another particle, so this is I and this is J. So if I exerts a force on J, then J will also exert an equal and opposite force on I. That means if Ij, this is always minus Fji. So due to this region, the internal forces cancels. Okay, so internal forces cancel each other from Newton's law. Okay, so what we get? The total force will be the external force. So what will be the result? M into ACM. This is obviously F external. Okay. This is the fundamental equation of center of mass. So what does this equation indicates? That the entire motion is described by this equation. Okay, and the externally applied force is acting about that particular point, that center of mass point. Okay, and the entire body as if something is concentrated at that particular point. Okay, so this is the fundamental equation of center of mass. Okay, this shows that the entire mass is concentrated at the particular point which is called center of mass. Okay, and the externally applied force always acting towards that point. Okay, so entire mass of the system is concentrated at center of mass. Okay, entire mass of the system is concentrated at center of mass, and the external force is acting about that particular point, that is on center of mass. Okay, so we see that the motion is completely described by the center of mass. Okay, so again I tell that what we conclude from this, that the entire mass is concentrated at that center of mass point and the externally applied force is always acting towards that point. Okay, so in our today's lecture I shall discuss about the center of mass theory and few numerical problems. Okay, so with this I completed this third chapter, conservation theorem. Now in my next class I shall going to start a new chapter. Okay, so if you don't subscribe my channel, then kindly subscribe it to get latest videos on physics, and the link of this video will be given in the description box. Okay, thank you.